Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into Google Drive, the cloud storage system that billions of users rely on every day to store, sync, and share their files. We'll cover how Google handles massive file uploads, intelligent chunking, deduplication to save petabytes of storage, real-time sync across devices, versioning, sharing permissions, and how it all scales to billions of users. Whether you're preparing for a senior engineering interview or building cloud storage infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into Google Drive, the cloud storage system that billions of users rely on every day to store, sync, and share their files across devices. If you have ever wondered how Google handles massive file uploads, intelligent chunking, deduplication to save petabytes of storage, real-time sync across devices, versioning, sharing permissions, and how it all scales to billions of users, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building cloud storage infrastructure, let's get into it. Here is the core problem. A user has 100 gigabytes of files across their laptop, phone, and tablet. They upload a 2 gigabytes video file from their phone while on a shaky 4G connection. Meanwhile, they're editing a document on their laptop that needs to sync in real time with collaborators. They share a folder with 500 people, each with different permission levels. Behind the scenes, Google needs to handle chunked uploads that resume after network failures, detect duplicate files across billions of existing files to save storage, maintain consistent file states across multiple devices, handle concurrent edits with conflict resolution, enforce granular permissions, and serve files instantly from edge locations. Any failure in this complex dance leads to data loss, sync conflicts, or frustrated users. The business needs a rock-solid cloud storage system that works seamlessly regardless of network conditions, device types, or scale. Let's walk through the functional requirements. First, the system must support file upload and download with automatic chunking, resumable transfers, and bandwidth optimization. Second, it must provide real-time sync across multiple devices with conflict detection and resolution. Third, it needs intelligent deduplication using content hashing to identify identical files and chunks across users. Fourth, it must implement versioning with unlimited history, rollback capabilities, and diff storage to save space. Fifth, it requires a comprehensive sharing and permission system with granular access controls, public links, and collaboration features. Sixth, it needs search and metadata indexing for fast file discovery. Seventh, it must provide offline access with intelligent caching and sync when connectivity returns. These 7 capabilities make Google Drive useful, not just storage. Now the non-functional requirements. The system must be highly available. Users expect 99.99% uptime for their files. Performance is critical. File upload should utilize available bandwidth, download should start instantly from edge caches, and sync should happen within seconds. The system must scale to billions of users and exabytes of data, requiring horizontal scaling and efficient storage utilization. Data durability is non-negotiable. Files must never be lost, requiring multiple replicas and erasure coding. Security is paramount. Files must be encrypted at rest and in transit, with proper access controls and audit trails. The system must be consistent. Users should see the same file state across all devices. Cost efficiency matters. Google needs to minimize storage costs through deduplication and compression. And finally, the system must handle network variability gracefully, from fiber to 3G connections. Here is the high-level system architecture. On the left, clients connect through API gateways to front-end services. Upload requests go to the chunking service, which splits files into fixed-size chunks, computes hashes, and streams them to blob storage via a distributed hash ring. The metadata service stores file metadata, user information, permissions, and version history in a distributed database. The sync service uses a publish-subscribe model to broadcast file changes across devices via WebSocket connections. The deduplication service maintains a global chunk hash table to identify and reuse existing chunks. The sharing service handles permission checks and access control lists. The search service indexes file content and metadata using inverted indexes. Background workers handle thumbnail generation, virus scanning, and content analysis. All services communicate through service meshes and are monitored by a centralized observability platform. The key metrics to memorize: cold upload throughput, measured in megabytes per second, with automatic bandwidth detection. Sync latency, the time from a file change on one device to appearing on others, typically under 5 seconds. Deduplication ratio, the percentage of storage saved through chunk-level deduplication, often 30 to 50% in enterprise environments. Storage efficiency, the ratio of logical storage to physical storage after compression and deduplication. API availability, the uptime percentage for all storage operations, targeting 99.99%. Cache hit ratio for downloads from edge locations, typically 85 to 95%. Conflict resolution rate, the percentage of concurrent edits resolved automatically without user intervention. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. A marketing manager uploads a 500 megabytes presentation from her laptop while on coffee shop Wi-Fi. The client chunks the file into 1 megabyte pieces, calculates SN256 hashes for each chunk, and starts uploading. The chunking service detects that 80% of chunks already exist in the system from other users' uploads and only streams the new chunks. Meanwhile, her phone receives a push notification about the new file and starts downloading the first chunks for preview. She shares the presentation with her team, granting edit permissions to some and view only to others. As collaborators edit the document, the sync service broadcasts operational transforms to merge changes in real time. When she goes offline on the subway, the app caches changes locally and syncs automatically when connectivity returns. Throughout this journey, the system maintains consistency, optimizes bandwidth, and provides a seamless experience. The core models and algorithms. Chunking uses content-defined chunking with rolling hashes to split files efficiently, ensuring similar files share chunks. Deduplication uses Merkle trees to compare chunk hierarchies without transferring data. Sync employs operational transformation or conflict-free replicated data types to handle concurrent edits. Versioning uses copy-on-write with differential storage, storing only changed chunks between versions. The permission model uses capability-based access control with inheritance and role-based permissions. Consistent hashing distributes chunks across storage nodes with automatic rebalancing. Erasure coding provides durability with configurable replication factors. The sync protocol uses vector clocks to detect and resolve conflicts. The key trade-off is consistency versus availability. Immediate sync provides better user experience but increases conflict risk, while eventual sync reduces conflicts but delays updates. Now the low-level design deep dive. The chunk storage layer uses a distributed hash ring where each chunk is mapped to a storage node based on its hash. Each chunk is replicated using erasure coding across multiple availability zones. The metadata layer uses a sharding database with user ID as the primary partition key, storing file metadata in document format. The sync service maintains a per-user operation log that records all file changes with sequence numbers. Clients pull this log via long polling or WebSocket connections. The deduplication service maintains a probabilistic Bloom filter for quick chunk existence checks before full hash lookup. The sharing service evaluates permissions using a cached access control list with TTL-based invalidation. Background workers process jobs from distributed queues for thumbnail generation, content extraction, and analytics. The system uses circuit breakers and exponential backoff for resilience and comprehensive metrics collection for observability. Key takeaways for your interview. First, cloud storage is fundamentally a distributed systems problem, so emphasize consistency, availability, and partition tolerance trade-offs. Second, always discuss chunking and deduplication, as the core storage optimization techniques that make cloud storage economically viable. Third, sync is the hardest problem. Explain how you handle network partitions, concurrent edits, and offline scenarios. Fourth, permissions and sharing are critical for collaboration systems, so discuss access control models and inheritance. Fifth, performance comes from intelligent caching, edge distribution, and bandwidth optimization. Sixth, durability requires erasure coding, geographic distribution, and comprehensive monitoring. If you can walk through this system with these 6 points, you will signal strong senior-level design thinking. That's it for Google Drive. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on Google Drive. We covered the full picture, from chunked uploads and deduplication, through real-time sync, version control, collaborative editing, and the low-level design of the storage layer and sync protocols. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.